Hello, welcome to Republic of Technocrats. I am your host Mr. Maverick. On the first episode of R.O.T Learners of Newer Technology of the Future, Mr. Matthew Purcell, the Senior Technical Trainer of A.I and Machine Learning, will talk about the basics of machine learning and its benefits.
Hi, I'm Matthew Purcell, a Senior Technical Trainer here at AWS, specialising in AI and machine learning. In this session, I'll take you through the basics of machine learning, starting from what is machine learning, through to the types of machine learning, what is deep learning, and an overview of the machine learning pipeline. We'll begin by taking a look at how machine learning can be used to address common situations more effectively than traditional programming approaches. Let's take a common use case. Product recommendations on a shopping site. Let's say you've been tasked with creating the back-end application that will provide product recommendations to customers based on their past purchases. Classical programming is traditionally how these needs were handled in the past. Programmers would set up rules that said, if this customer purchased product X in the past, show them product Y, because there was some established relationship between those two products. While this can occasionally prompt customers to make that second purchase, it required programmers to explicitly define and set these rules. They couldn't take very much additional context about the customer or products into account. In addition, customers are unique, and just because one customer was interested in products X and Y, that doesn't mean most or even many customers will be interested in both products as well. Finally, even if we were to spend the time developing more complex prediction rules whenever a recommendation needed to be made, the application would have to run through all of the appropriate rules all over again. As more rules are added, the process takes longer to return a result, meaning customers are waiting for those recommendations to load and likely getting frustrated and moving on to another page. Machine learning, by contrast, would let us use a variety of data collected in the past to automatically derive the patterns hidden in that data. The patterns are then used to create the model, which is applied to new data to provide a more well-informed and adaptive prediction. In this example, we'd be able to use the customer's purchase history in combination with the data of customers and sales site-wide. We can use machine learning to identify the patterns between past customers and sales, then apply those patterns to new customers in order to provide better recommendations. So, what is a model exactly? A model in machine learning is the trained algorithm that you use to identify patterns in your data. The key there is that it's trained through the machine learning process. It isn't created manually by programmers setting out rules, like in classical programming. Let's look at a very simple example algorithm. This has been simplified from what you might use in a real environment, but it shows what are the two key components of an algorithm: features and weights. Now, don't be too scared because there's a bit of maths here. This is actually quite simple, and we're going to step through this together. Features are parts of your datasets that are identified as important in determining accurate outcomes. For example, with our product recommendation algorithm, the first feature might be whether or not the item is a hat. These features have to be expressed mathematically, so in this case, our model will convert a yes to a 1 and a no into a 0. But key to machine learning is this idea of context. That's where weights come in. Weights represent how important an associated feature is to determining the accuracy of the outcome. So something that has a higher likelihood of accuracy has a higher weight and vice versa. In this case, our model has been trained and has determined that because the customer has purchased 8 hats in the past, that translates to a weight of 0.8. It's important to note this is a very simplified version of what really goes on. As this session continues, your understanding of weights and features will grow in depth. But for now, this is the most critical part of understanding how weights and features work in an algorithm. Now let's look at the next set. The second feature has to do with whether or not a product is from a particular brand. The product is from that brand, so that converts a gain into a 1. The second weight says that since 2 out of the 8 items this person bought in the past were from that brand, that translates into a weight of 0.25. If this was a very simple model, this is what you would end up with. Let's say the standard for whether or not to recommend is if the final result is greater than 1. The model performs this calculation and finds the final value to be 1.05. Therefore, this product is an acceptable recommendation. So if we're not using a traditional programming approach, you might be wondering what types and kinds of algorithms are actually used for machine learning. Before we look at the kinds of algorithms, let's take a step back and look at the different types of machine learning. There's supervised learning, where a model uses known inputs and outputs to generalize future outputs. There's unsupervised learning, where the model doesn't know inputs or outputs, so it finds patterns in the data without help. And there's reinforcement learning, where the model interacts with its environment and learns how to take actions that will maximize reward. Finally, there's deep learning, which is a subset of machine learning. These algorithms learn by using artificial neural networks, which we'll talk about in a bit. Again, it's important to know the types of machine learning because the type will guide you towards selecting an appropriate algorithm or algorithms that make sense for solving your business problem. First, let's talk about supervised machine learning. Supervised learning is a popular type of machine learning because it's widely applicable. It's called supervised learning because there needs to be a supervisor, a teacher who can show the right answers, so to speak. Like any student, a supervised algorithm needs to learn by example. Essentially, it needs a teacher who uses training data to help it determine the patterns and relationships between the inputs and outputs. Like here in this picture is a car, and here is a car in another picture. The model is trained on this labeled data so that it can accurately identify where a car is in a new picture it hasn't seen before. But within supervised learning, you can have different types of problems. These can be broadly categorized into 2 categories, classification and regression. So think of machine learning problems as falling into one of these 2 categories. Within classification problems, there are actually 2 types. The first is considered a binary classification problem. Think back to the example provided here about identifying fraudulent transactions. The target variable in this example is limited to 2 options, fraudulent or not fraudulent. This is an example of binary classification. You're classifying an observation into one of 2 categories. There are also multi-class classification problems. These machine learning problems classify an observation into one of 3 or more categories. Let's pretend you have a machine learning model that predicts why a customer is calling your store so that you can reduce the number of transfers needed before getting the customer to the right customer support department. The different customer support departments in this case represent a variety of potential target variables, which, needless to say, could be many different departments, far greater than just 2. There are also regression problems. In a regression problem, you're no longer mapping an input to a defined number of categories, but instead to a continuous value, like an integer. One example of a machine learning regression problem is predicting the price of a company's stock. For example, here is a regression-based algorithm predicting that tomorrow, the stock price for a company will go up from $113 per share to $127 per share. Now let's talk about unsupervised machine learning. Sometimes all we've got is the data. There's no supervisor in the room. In unsupervised learning, labels are not provided like they are with supervised learning. We don't know all the variables and patterns. In these instances, the machine has to uncover and create the labels itself. These models use the data they're presented with to detect emerging properties of the entire dataset and then construct patterns. A common subcategory of unsupervised learning is called clustering. This kind of algorithm groups data into different clusters based on similar features, and that helps better understand the attributes of a particular cluster. For example, by analyzing customer purchasing habits, unsupervised algorithms are capable of identifying groups of customers that identify a particular company as being large or small. It may be sufficient for smaller companies to purchase basic cloud hosting resources, while larger companies may be more likely to purchase entire cloud solutions, including advanced security, dedicated private connections, virtual private clouds, and more. Clustering in this situation might help you realize that you need to come up with a different marketing strategy for different sized companies. The advantage of unsupervised algorithms is they enable you to see patterns in the data that you otherwise were unaware of, like the existence of two major customer types. One use for unsupervised learning is anomaly detection, such as this speed camera example. This model is designed to detect potential hardware failures for speed cameras by looking at anomalies in the data. In a classical programming solution, every data point outside of a clearly defined boundary would have to be evaluated as a potential failure. But with unsupervised learning, models can identify what are simply like outliers, such as people driving at very high speeds at random points during the day, and what is more likely to be a result of hardware failure, a high volume of extremely high speeds recorded over a span of time. Now let's talk about reinforcement learning. Take the example of AWS Deep Racer shown here. In the AWS Deep Racer simulator, the agent is the virtual car, the environment is a virtual racetrack, the actions are the throttle and steering inputs to the car, and the goal is completing the racetrack as quickly as possible and without deviating from the track. The car needs to learn the desired driving behavior to reach our goal of completing the track. To learn this, we will use rewards to incentivize our model to learn the desired driving behavior. In reinforcement learning, the thing driving the learning is called the agent. In this case, it's the Deep Racer's car. The environment is the place where the agent learns, which in this example would be the marked racetrack. When the agent does something in the environment that provokes a response, such as crossing a boundary it shouldn't cross, that's called an action. That response is called a reward or penalty, depending on whether the agent did something to be reinforced or discouraged in the model. As the agent moves within the environment, its action should start receiving more and more rewards and fewer penalties until it meets the desired outcome. Now that we've talked about the three categories of machine learning, let's talk a little about deep learning. Deep learning, or DL, is a subset of machine learning. These algorithms learn using artificial neural networks. Let's dig into that a little. Deep learning represents a huge leap forward in the capabilities for artificial intelligence and machine learning. While the theory for deep learning goes back decades, the hardware required to run deep learning problems wasn't generally accessible until very recently. But now that it's available, we're able to use deep learning to address problems more complex than we could before. To demonstrate the leaps between these three categories, we can use the classic example of machines that can play chess. With classic artificial intelligence, the machines couldn't learn anything that wasn't given to them, and that had to be directly done through code. So a machine could play chess based on the rules they were provided, but any improvements to its strategy would have to come from a programmer explicitly calling them out and programming them in. With machine learning, as we've learned in this session, chess playing machines can actually learn and improve their chess skills by doing things like analyzing past chess games that were played by humans. They could be provided with simple chess strategies, but then use something like traditional reinforcement learning, where they can identify patterns in moves that were more likely to result in winning versus moves that were more likely going to result in losing the game to hone their performance. But now with deep learning, we're able to create machines that can learn chess in a fashion more like humans learn it, by playing. A deep learning machine could be given the most basic rules on how chess is played and use its complex, layer-based, iterative approach to learn its own chess strategies and recognize patterns several orders of magnitude more complex than a traditional machine learning model could. The deep learning models in use today rely on things called artificial neurons. These are math functions that receive inputs and sum them up to create an output. Work on artificial neurons began back in the 1940s. However, it wasn't really until technological breakthroughs in the 2010s enabled artificial neural networks to be used in real environments. In an artificial neural network, or ANN, each layer summarizes and feeds information to the next layer, ultimately producing a final output or prediction. During this process, the model derives the features itself. Now, we've talked about features, their importance, and how they're used in classical programming. Let's look at how the use of features evolved from classical programming to machine learning to deep learning. As we've established before, in machine learning, the features are manually engineered and then used to train and develop the model. But in deep learning, the features are derived by the artificial neural networks itself during the training and tuning process. The performance of the model based on that training is then fed back through the artificial neural networks iteratively until generating the final model. Let's break this down into a more concrete example of deep learning analysis of an image. In this example, we see that the machine starts by identifying specific features of the input, beginning with pixels. From there, it identifies edges, corners and contours, and object parts before making a prediction as to what the object is. In this way, it's extracting features like edges, corners, and parts automatically based on the algorithm and data it's being trained on. It can identify patterns at levels the human eye can't easily identify. Again, the premise for deep learning started in the early 20th century, but the impacts of improvements made in the field was really felt in the early 2000s. The big shift began with the ImageNet Large-Scale Visual Recognition Challenge, or ILS VRC, which was a competition where research teams submitted programs that classified and detected objects and scenes in photographs. In 2010, the first year of the challenge, the winner of the challenge had a model with an accuracy rate of 71.81%. In 2011, the next year, accuracy improved marginally to around 74%. In 2012, when deep convolutional neural networks, common in deep learning models, started to be used, the accuracy rate jumped up to about 82% and has been steadily climbing ever since. Then in 2015, the winning program actually exceeded human performance at these narrow ILS VRC tasks. Let's now pivot towards the machine learning pipeline by walking you through the pipeline phases. So to begin, you should always start with the business problem you or your team believe could benefit from machine learning. From there, you want to do some problem formulation. This phase entails, in part, articulating your business problem and converting it into a machine learning problem. Again, we'll get into more detail later on, but for now, let's just generally talk about what's going on. After you've formulated the problem, you move on to the data preparation and pre-processing phase. Data preparation and pre-processing includes a few important aspects. Data collection and integration in order to ensure your raw data is in one central accessible place, and data pre-processing and data visualization, which involves transforming raw data into an understandable format and extracting important features from the data. All this is done to ensure that your data is formatted correctly for your machine learning algorithm, and that your data is cleaned up in a way that will maximize your model's prediction power. Once those steps are complete, you are ready to train and tune your model. This is an iterative process that can be performed many different times throughout this workflow. Initially, upon training, your model will probably not yield the results you might be expecting. Therefore, you will perform additional feature engineering and tune your model's hyperparameters before retraining. This cycle is repeated until your model's evaluation shows it is performing at the level required by your business case. If your model doesn't meet your business goals, you will need to go back and reevaluate a few things. Take a second look at your data and features for ways to improve the model and the way it's produced. Building a model usually is an iterative process in this way. Once the retraining happens and you're satisfied with the results, your model is deployed to deliver the best possible predictions. But this is often a tedious and manual effort. So the bulk of this discussion is designed to walk you through these different phases and to give you hands-on experience with each of them. So let's start with an example close to home for us here at Amazon. Several years ago, Amazon needed to improve the way it routed customer service calls, so it looked to machine learning for help. The original routing system worked something like this. A customer would call in and was greeted by a menu. Press 1 for returns, press 2 for Kindle, press 3 for, well, you get the idea. The customer would then make a selection and be sent to an agent who would be trained in the right skills to help the customer. During the problem formulation phase of the pipeline, Amazon determined that the current routing system was problematic. Thinking about Amazon, you might be able to guess that we do and sell a lot of stuff here. So the list of things a customer might be calling us for is, well, just about endless. So if we didn't play the right option to a customer calling in, the customer might be sent to a generalist or even to the wrong specialist, who then had to figure out what the customer needed before finally sending them to the agent with the right skills. For some businesses, maybe that's not the end of the world, but for Amazon, we deal with hundreds of millions of customer calls a year. So it was pretty inefficient and it cost a lot of money, wasted a lot of time, and worst of all, it was not a good way to get the customers the help they needed. So the business problem that was articulated at this phase was focused around figuring out how to route customers to the agents with the right skills and therefore reduce call transfers. To solve this problem, we needed to predict what skill would solve a customer call. Converting this to a machine learning problem, this became identifying patterns in the customer data that we could use to predict accurate customer routing. Based on the wording of this machine learning problem, it was clear we were dealing with a multi-class classification problem. Since we wanted to base our predictions on past data from customer service calls, we were dealing with supervised learning. We would eventually train our model on a bunch of historical customer data that included the correct labels or customer agent skills. That enabled the model to make its own predictions on other similar data moving forward, predicting, say, that a customer needed a Kindle skill. The data we needed for this came from answering questions like, what were customers' recent orders? Did customers own a Kindle? Were they Prime members? And the answers to these questions became our features. We then moved on to the data preparation or pre-processing phase. This phase, as we'll detail later, includes data cleaning and exploratory data analysis. Now, a lot was done at this point, but one example of data analysis undertaken at this point was to think critically about the labels we were using. We asked ourselves, are there any labels we actually want to exclude from the model for some business reason? Are there any labels that are not entirely accurate? Are any labels similar enough to be combined? Finding answers to some of these questions by exploring the data would help cut down on the amount of features being used and simplify our model. An example of what might have been found in this types of analysis was instead of having labels representing multiple Kindle skills, it made more sense to combine those skills into one overarching Kindle skill label, so that every customer who had a problem with a Kindle was routed to an agent trained in all Kindle issues. Data visualization was the next step, where we did a number of things, including a programmatic analysis to give us a quick sense of feature and label summaries, which helped us effectively understand the data we were working with. At this point, we may have noticed that 40% of calls were related to returns, 30% were related to Prime memberships, and 30% were related to Kindle, and so on. Important information that gives us a better sense of the data that we're working with. We then moved on to feature engineering. We had some features that answered questions like, what was a customer's most recent order? What was the time of a customer's most recent order? And did the customer own a Kindle? When we fed these features into the model training algorithm, it can only learn from exactly what we show it. Here, for instance, we are showing the model that this purchase was made at 1 p.m. on Tuesday the 13th. Unless we want to predict something really specific, or we're doing a time series analysis, that might not be the most useful feature to feed into our model. It would be more meaningful if we could transform that timestamp into a feature that represents how long ago that order took place. Knowing, for instance, that your last purchase was months ago will probably help the model realize that your last purchase probably isn't the reason that you're calling. Obviously, we can engineer this feature by just taking the difference between the order date and time and today's date and time, and now the resulting feature is much more helpful. A big part of preparing for that training process is to first split your data to ensure a proper division between your training and evaluation efforts. Think about it this way. The fundamental goal of machine learning is to generalize beyond the data instances used to train models. Yeah. You want to evaluate your model to estimate the quality of its predictions for data the model has not been trained on. However, as is the case in supervised learning, because future instances have unknown target values and you cannot check the accuracy of your predictions for future instances now, you need to use some of the data you already know the answer for as a proxy for future data. Evaluating the model with the same data that was used for training is not useful because it rewards models that can remember or memorize the training data as opposed to generalizing from it. A common strategy is to split all available labeled data into training, validation, and testing subsets, usually with a ratio of 80%, 10%, and 10%. Or another common ratio is 70%, 15%, and 15%. After running a training job, we evaluate our model and begin a process of iterative tweaks to the model and our data. For instance, we performed hyperparameter optimization. We tweaked the learning parameters to control how fast or slow our model was learning, because learning too fast means the algorithm will never reach an optimal value, while learning too slow means the algorithm takes too long and may never converge to the optimum given the number of steps involved. Once happy of how the model interacted with that unseen test data, we deployed the model into production and monitored it to make sure that our business problem was indeed being addressed. Our problem was predicted on the assumption that the ability to more accurately predict skills would reduce the numbers of transfers a customer experienced. That was put to the test after we deployed, and in fact the number of transfers did decrease, resulting in a much better customer experience. We then deployed the model, and it now helps customers get directed to the correct agent the first time. So, where to from here? AWS Training and Certification provides several training offerings to improve your knowledge, understanding, and how you can use machine learning to solve your business problems. Head across to AWS Skill Builder, where you can find free, self-paced digital training courses covering a variety of topics, which includes machine learning. We also offer instructor-led classroom courses, such as the Machine Learning Pipeline on AWS, which you can find more information about on the AWS Training and Certification website. Finally, if you don't know where to start, check out the Machine Learning Learning Plan on AWS Skill Builder. This brings together a variety of our machine learning courses in an easy-to-navigate learning plan to help you map out your learning journey. In this session, we talked about the basics of machine learning, starting from what is machine learning, through to the types of machine learning, what is deep learning, and an overview of the machine learning pipeline. I'm Matthew Purcell, and it has been my pleasure to bring you this presentation. Thanks for watching, stay active, stay healthy, and I look forward to hopefully seeing you again in a future session.